So let's take a look at that slide I mentioned regarding the TCP header. Now here's again the word format here of 0 through 31 bits inside the TCP header. If you take a look at all the different parts and pieces of the TCP header, it starts and leads off with a source port. Now the source port generally is a random number coming from your client-side application and is again randomly generated as a number above 1023 within the TCP IP values here. So because it's 16 bits in length, you're going to have a value between 0 and 65,535, and that random source port generated by your client application will be something above 1023. And the reason why, and you may be thinking about this, the reason why it's a random number in the source port generally is because, well, it needs to understand where it's going. For instance, if I were to say, what's the port number for web traffic, right? You'd think, well, it's port 80. Well, it's port 80 on the server side. What is it on the client side? Client side is a random number. And if you think about the logical reasons why, have you ever opened more than one window to, say, Google? How would it know which window to fill the information to as it responded back if you had 6 or 7 windows open to a website like Google? So in that particular case, the random source port allows us to open multiple application windows pointing to the same server, and that server all listening on port 80 or whatever well-known port number on the destination side. So the destination side should be your well-known port number, at least in the transmission side of going from the client to the server. Now when the server responds back, it's going to switch those. So the source port will then be port 80 or whatever well-known port it is, and the destination will be the random generated port that your client application did. So TCP messages, again, could have those values on either side depending on the direction. It's bidirectional communication here. So these port numbers are key to identifying which actual applications are communicating at the layer 5 through 7 of the OSI reference model. So the next two fields within the TCP IP header is specifically the sequence numbers and the acknowledgement numbers. Now the sequence numbers, we're going to send a certain amount of data and identify it with sequences, and then we expect an acknowledgement back. Now the number of sequences we send, the number of segments we send, will depend on something else, and that's a field, not exactly the next field, but it's the window size field in the next word. Now the window size field identifies how many sequences we're going to send before we expect an acknowledgement. And that acknowledgement will be forward acknowledgement. I got some graphics on how that actually works here in a few slides. But the idea here is we're not going to do a one message to one acknowledgement type scenario. So I'm not going to send one sequence and expect acknowledgement and a next sequence and expect acknowledgement. We have a window size that builds as the connection increases. So as we send more and more data, we build and increase that window size so that we can send more data without expecting an acknowledgement back. That is one of the failings of TCP, that the slow start mechanism for the window size actually slows down our initial data transmission in the beginning as it ramps up and attempts to increase the window size larger and larger value. All right, so in the next word, I already mentioned the window size portion. There's the code bits portion, which is the beginning portion of that word, has things like the header length. There's some reserve fields in there. And then a bunch of bits that are being set there that are used for establishing and tearing down of a communication. Particularly the SYN, reset, FIN, ACK bits are the ones that we'll commonly talk about. The SYN bit or synchronization bit is used to establish the communication. The acknowledge bit will then acknowledge that we're attempting the communication. The reset and FIN bits, finish or reset bits, are used to tear down a communication during the 4-step teardown process to tear apart a TCP session. There's a TCP checksum field, which allows us to check to make sure the data hasn't been molested in transit. There's an urgent pointer, sort of a layer 4 QoS mechanism, one that we rarely use. Usually when we're doing QoS, we'll focus on the IP header TOS bits, the TOS bits that are there, and then we'll also worry about the layer 2 bits if necessary for our QoS mechanism. So it's not very common for us to use the QoS mechanism available to us at layer 4, even though they're there in the header. there's an options field, and then the remaining data that we have within the application that we're building and carrying this information between two endpoints.